Hello everybody, this is Ryan. I've got another example, this time of a dewatering problem for the construction engineering course. So here's the problem right here. You can go ahead and pause it and read through it. Might look a little bit familiar. This should be in a slightly easier format to make out just so we can get moving on it. So this one, you can see what we're going to try to do is find the depth and slope of the draw, so that's H and M. Selecting a pump, we're going to find the flow during steady state for this, given a given K value, and then we're going to select a pump for the steady state as well. So let's go ahead and get on into this and get started. You can see what part A was, which is pretty similar to other part A's that we have had. So let me pick a good one here. So we're going to just start out with our equation here. Really, it's H prime equals H minus M S over 2, and that's the spacing. Okay, so here we don't know M, we don't know H. That's what we're trying to find. We do know H prime. In this problem, you basically have the ground level right here. The water table is 7 feet below it, and we want to go for a final excavation depth H prime of 11 extra feet. So 18 feet total will be our excavation depth. And then this right here should actually be going a little further, because you know how this works. As these two cross over, we'll get our effective H prime. So H is going to be all the way down from there to there. So that's what we're going to try to find first. Alright, so back to it. There's our equation. H prime equals H minus M S over 2. And we know that S in this case is equal to 4. So we're going to have H prime equal H minus M, and S over 2 is 2. So just to simplify that even more, we have 11 being H prime equals H minus M times 2. And this will be equation 1 that we'll stash away for now. The other equation that we use here is that for flow. If you remember, flow equals Q equals Ka. So Ka is the permeability, which I didn't actually write down in there, but I'll give it to you right here. And then A is the area of the conical surface, since we're using a simplified conservative method. So here, based on previous discussions, our area is equal to pi A over M. I'm sorry, that should be H. Pi H over M. Okay, H. Oh, we were doing blue. Oh well. Square root of H squared plus H over M squared. I'm not going to explain where these came to today. You can go ahead and look back at your notes for that one. Alright, so there's the area. And then just going back to this equation, Q, we were told in the problem we were going to be using 190 GPM pumps. K, and this I didn't give you, but it's for this problem, 5.13 times 10 to the minus 4. And that's in feet per second. Is the units there. So let's go ahead and convert that, because we're already in gallons per minute and we got feet per second. So let's go ahead and multiply 60 seconds in 1 minute. And then this whole thing times the area. So Q equals Ka. And A we saw from up here, right? Up here, and so we get an A value. If we solve this out right here, divide 190 by this number, we get A equals 827.16. 27.16, and that's square feet. That's the surface area. Okay, so using that, we can plug back into this guy here, and we get 827.16 feet squared equals pi h over m. Oh, now I'm back to blue. Interesting. Square root h squared plus h over m squared. Okay, so this is equation 2. So equation 2 now, let's go back to black. I don't know why I keep switching. So now we've got equation 1 is in terms of h and m. Equation 2 is all in terms of h and m. This is pi. That's a number we know. So all h's and m's. So we solve those two equations simultaneously. I won't do that here in the interest of time, but I'll just write solving 1 and 2. We get h equals 12.85 and m equals 0.92. Okay, that's feet, and that's a slope, so it's unitless. Okay, so that's part A right here. We've got our solution to part A. All right, so B, going back here, was to select a pump for this initial draw, and it kind of gives us some stuff. 3 pumps capable of 190. So looking at that, we're going to assume 0 friction, so our head is just going to be h. It's going to be 12.85 feet, and looking here, our height above is about 7 feet, so we'll just use 10 feet as height above the water surface. So if there's 3 of them, let's go to, that's not it. Let's go to this guy, and we've got a chart here. So looking at this chart here, try to get it centered for us. Can't really read what it says here, but if you go to page 680 in your book, chapter 19, you'll see that this up here gives you the model number. This gives you the height above the water. This is the total head. So if we just look at this one right here being our, actually this one right here is the one we want. This is our 18M right here. So if we just use 10 feet, actually we can use 20 feet as the head if we want, just to be super conservative. And then if we go over to, let's say 10 feet here, the max capacity for that one's 259, and we were only trying to get 190. So that means that we are okay. So if we go back here, those 3 for part B here, 18M will work. Okay, so let's move on. Part C. Part C here was the flow needed during steady state. So let's look at the steady state condition real quick and go ahead and do that calculation. So the steady state here starts with calculations starting with this equation, R0, which is on the chart, h over m. Okay, so using what we know about those, that's 13.97 feet. And then using the equation for L prime equal to h squared plus h over m squared, square root of that, sum equals 18.98 feet. Then we get the area total from this equation here, we have 2L, and this is a capital L, plus R0 times L prime plus 2W plus R0 L prime. Okay, so this is the length being the entire length of the excavation site and width being the entire width. So in this problem, it's 120 feet by 120 feet. So plugging that all in there, using R0 from up here, using L prime from right here, L and W both being 120, we get a total area of 10,171.61 square feet. So that's the total area for the entire excavation. And we know that Q equals KA. So using this total, put a T here, this is going to put our needed Q, our needed flow rate in order to keep the steady state. So using our K value that I mentioned above, 5.13, 10 to the negative 4 feet per second, okay, times our area from right there, 10,171.61 square feet. Let's go ahead and change this into gallons per minute here. So we'll get 60 seconds, 1 minute, and then let's change the cubic feet here. So it's 1, we'll put cubic foot is equal to 0.134 gallons. Okay, so doing all that conversion, we end up with a Q needed of 2,336.43 GPM. So there's part C. That's what we needed for part C. Okay, so yeah, we can do a couple things here. Kind of depends on your assumptions and a few other things. But we're going to make the assumption for this problem that basically we're going to use the pumps from the initial drawdown and add some pumps. So if we use those 3 pumps at 190 that we already sized, if we're running them at 190, okay, so using those 3 pumps from before, we go ahead and calculate that out. We get 190 times 3, 570. So 570, this pen does not want to play along. Anyway, so there's 570 from the initial, subtract that off of this 2336, and the remainder we're going to just assume initially that we're going to use 4 pumps, so 4 additional pumps, and if you do the math, it comes out to sign 441. I'll get this pen working eventually. Okay, so 441.61 GPM. Okay, so that's the additional pumps, and these are what we're going to design here on the next step. Okay, so keep that number in mind. Alright, so coming here, then we're going to do the friction calculations. Okay, so basically what we've got here is going to table 19.10, and looking at the 6-inch side of things, we get that we have one check valve. That's in the problem here. It says right here, one check valve, 3 90-degree elbows, 6-inch steel pipe, 200 feet away from our leach point. Okay, so one check valve going to that table is at 63 feet is the equivalent. 3 90-degree elbows at 6-inch comes to 48 feet. Okay, and then we have the additional length to the leach field here of 200 feet. So adding all those together, we end up with 311 feet is our equivalent, total equivalent. Okay, so keeping that in mind, we want to now look at the friction loss per 100-foot length. And that's from table 19.9, which I think I can find here. Yep, right here. Okay, so we're basically looking at the 6-inch column. Over here is the flow, which in this case we're going to use the flow of 441. You can see here that we have a couple different values, so we're going to have to interpolate. So coming across, looking at the 6-inch, we're going to be using these values here. So that's just how you find it. Okay, so coming back here, if we interpolate, the 400 value was 1.4. We're using 441.61. X that we don't know. 500 is 2.2. So doing our math here, 41.61 over 100. Equals x minus 1.4 over 2.2 minus 1.4. So we get our value is going to be 1.73. So 1.73 for every 100 feet. So if we take our 311, multiply it by 1.73 per 100 feet, we end up with 5.39 feet. And that's the head loss. So we have our total head then, that's due to friction, is our original head, we're coming up 11 feet, plus the friction head. So we get 16.39 feet. Okay, if we look at now the table using this 441, going back to table 19.8, we looked at our initial draw pumps, we checked those out. Now if we use 20 foot ahead, just rounding up to be even more conservative, and 10 feet above the water based on what we had, we can look at the table Okay, so this table, here it is. Okay, there we go. Okay, so we can look here and look for where the total head, 20 feet, and the height from water of 10 feet gives us an allowable value. So coming over here, it basically be here. That's plenty. That's even better. But those are probably more expensive. Let's look at the cheapest one that'll work. So 333, not quite. We're looking to get 441. So it looks like our best bet is right here, which is going to be our 40M, which you can't read, but it's the 40M. So for this, I'm going to say we're going to use the 40M. And I believe we have 4 of those. So 4 40M pumps. And it's going to be different for everyone. You can do it, you might have to iterate, etc., to get different solutions and based on your different, um, you know, problem setup and what you decided to do. So that's it. There's a little bit of info, give you an idea about dewatering.